So I'm happy to be here today, and I will show you how Knime can make your structure-based virtual screening campaign more successful. So first of all, I would like to make a disclaimer. This presentation is not about structure-based virtual screening itself, but the step before, the calibration. So if we do an analogy, it will correspond to the pilot screen of a HTS campaign during when we can evaluate some parameters before doing the real throughput screening campaign. So the calibration of structure-based virtual screening is really a key phase because it will impact the quality of the following SBVS. And by the way, it should also increase the hit rate. The goal of the calibration process is to be automatized, standardized, and shared. It's why Knime is really a nice platform to develop this type of process. Finally, the evaluation of different parameters should permit to choose the best protocol. I mean the best combination between of protein structure, docking software, and scoring function for the real SBVS campaign. This workflow is published on the Hub, and the reference paper is at the bottom of this slide. So here you can see the whole workflow, so you don't need to read it. It's just divided in 4 sections. The first section is about the decoy generation. I will go deeper into it in a few minutes. Then in the second section, by using docking and rescoring outputs, you will generate some raw curves. In the third section, you will calculate some MSD between the docking poses and the reference co-crystallized binding mode to have an idea of the ability to retrieve a binding mode. And in the last section, you will plot some the AUC against MSD to easily select the best compromise protocol. So in this presentation, I will focus on the first section of this Knime workflow. But before moving to that, I want to mention some general information and best practice to generate decoys and raw curve. So I will begin by some highlights about the decoy generation. So what is a decoy? Classically, it's a molecule that won't bind to your target. So in 2006, the Society team published a first paper around benchmarking sets for molecular docking. And then they did a release in 2012 and is now called the DUDI database. So this database does contain a limited number of targets, around 100, from kinase to nuclear receptor families, but not only. So why do we want to generate decoys? So in some projects, sometimes we don't have inactive compounds. So we need to generate virtual inactive compounds to be able to build some raw curves and to compare docking model performance. So I will give you a better explanation of what is a raw curve in the next slide. And how to generate decoys. So you can follow the rules given in the DUDE publication. So you will use some real inactive real active compounds, and you will go into a huge database to search for compounds with the same physicochemical properties, but dissimilar fingerprints. It means that you want to be in the same chemical space, but you want some compounds with totally different topology. So how many decoys do you need to generate for your raw curves? So 10 decoys per active should be enough. In the DUDI, it's 50, but in a recent paper that I put here at the bottom of the slide, they compare 2 different decoy set size. So one active for 64 decoys or one active for 6 decoys, and there is no meaningful difference in the raw curve generation. So now I would like to explain rapidly what is a raw curve. So here you can see different raw curves with the different colors. It will give you the possibility to see at a glance the performance of your classifier. So it is a false positive rate versus the true positive rate. And the perfect classifier here in blue will permit to retrieve all active compounds before inactive compounds. Then in orange, you can see the AUC, it's area under the curves. It will give you the global model performance. It is a value between 0 and 1, and bigger is the better. And what is the value of using this type of graph and value for SBVS calibration? It will permit to compare different protocols quickly and to find the best protocol that will enrich the first part of your ranked database in active molecules. So here is a so now different situations can occur in your projects because sometimes you don't have active compounds. So you won't be able to use this Knime workflow. Instead, you can proceed with some consensus using different scores, docking scores. If you have active compounds and you also have some inactive compounds, you can directly use the workflow. You don't need to generate decoys. Then if you don't have inactive compounds or you don't have enough inactive compounds, you can check if your protein target is already in the DUD. If yes, you can retrieve some decoys from the DUD. And if no, you can use the first section of the workflow. So it's what I will focus my talk now on this part. So here you can see a focus on the first section of the workflow. This section can be used by anyone because all the chemistry nodes that are used there are from RDKit, that is open source. So how it works. As a first step, you will need to put a SD file with your active compounds and then the 5 descriptors, so molecular weight, log P, H-bond donor, H-bond acceptor, and rotatable bond will be calculated, and also the RDKit fingerprint. The same will be done for database. So it can be the database you want to screen in your real SBVS campaign, but it can be also some random compound from the Zinc database. So from this database, we will calculate the same type of parameters, descriptors, and fingerprints. And then for each active molecule, we will loop and we will filter the database, keeping only compounds that are in the range for the physico-chemical properties. And then we will compare the fingerprints and keep the most dissimilar fingerprints. So we will sort by increasing similarities. Sometimes in your project, your active compounds can be really similar to each other. So it will lead to pick the same decoys at the end. So to ensure that we end up with 10 decoys per active, after this loop, I added another recursive loop to ensure that we have only 10, we have 10 decoys per active. So now I would like to show you a case study around a nuclear receptor called retinoid X receptor alpha. Concerning the input data used for the setup, we had first to clusterize the 57 PDB structures available. So for this, we consider all atoms of the pocket residues and we calculated the SD between all the pairs. You can see here the range from blue to red. So blue is RMSD equals 0, so really similar structures, and red is dissimilar structures. So you can see that 4 clusters appeared, and we pick up the best resolution structure per cluster as a representative structure. Then, as for the active compound, we retain the 33 co-crystallized ligand, and then we generate 330 decoys through the first section of the workflow. Concerning the tools we use in this workflow, so as I already explained in the first section, it is RDKit nodes, so they are open source, and so everybody can use it. For the other section, you will have to adapt it to the software you have, because at Evotec we had Gold. For the docking, we have some in-house specific Gold nodes that are linked to our cluster. And using Gold, we have 4 different docking functions: ISP, PLP, ChemScore, and Gold Score. Then we generated 10 docking poses for the docking part, and then all the docking poses were rescored using the MoCCG complex scoring nodes. And in the node we can have 5 different rescoring function: Affinity DG, Alpha HB, IC, GBVI, WSA, and London DG. And the 6th possibilities is to not rescore the output from the docking. And for the ability to retrieve a co-crystallized binding mode, we use the MoCCG RMSD node, but I know that some open source companies also propose some RMSD calculator node. So concerning the output data, we have nearly 100 combinations, because we evaluated 4 structures, 4 docking functions, and 6 rescoring possibilities. So here you can see the legend, so the shape for the docking function and different color for scorings. And you have 4 plots, 1 plot per structure, protein structure. So what we can see is that the results are really dependent on the protein structure. But you can also say that this structure is belonging to the biggest cluster. And then you can see also that the results are heavily dependent on the docking and the rescoring. So the best combination is this one. So the structure is 1MVC, docking algorithm is ChemScore, and the rescoring function is Alpha HB. I would like to go deeper in this result, so I will focus on structure 1MVC and docking ChemScore, and to look to the enrichment curve and to be able to see the impact of the rescoring. So you can see that rescoring has a huge effect. It really permits to sort, so some rescoring function like Alpha HB and London DG can really improve the results, but sometimes other rescoring function can also give worse results. So you should carefully use the rescoring during your SBVS campaign. So to finish, I want you to keep in mind that the calibration step is really key. As you have seen, your result will be highly dependent on the PDB structure you select, the docking algorithm, and also the rescoring function. So by doing this setup, you will gain in quality, because you will identify the best parameters to use for your SBVS, and you will be able to clearly report it, what you did. You will gain a lot of time, because all the steps are automated through the Knime workflow, and it will be easy to share with your colleagues. And to finish, this workflow is really an easy way to homogenize your setup and to adapt it to your preferred docking software. So this work has been done at Evotec in collaboration with Martin, Ogdulia, Claudia, and Constantino. It was also a part of a lean project, so where Daniel gives me a great help. And thanks to this project, we were able to evaluate all the benefits of using Knime. I would like also to thank Discngine to support me for this presentation, and you for your attention. So I would be happy to answer some questions now.
Thank you, Emilie, very much. That was a very interesting presentation. And we already have some questions. So for the rest of the guys who did not put their questions there yet, please use the Q&A session of the tool. And so we have the first question to you, Emilie. Knime is a big fan of open source. Is this workflow available already on Knime Hub, or will it be? Will you make it public? How is that?
Yeah, the workflow is already available on the hub. And I also worked with Ogdulia on another workflow for covalent docking for gold, preparation of a ligand for covalent docking that is also available on the hub. I think if you search for Evotec keyword, it should appear.
That's fantastic news. Thank you very much. We have a second question for you. You mentioned that you are generating some physical chemical properties and descriptors for the molecules. Do you use them for any kind of filtering later on?
Yeah, it's so for the Decoy generation, yes, because it's the first part. I don't know if it is the sense of the question, but yes, it's so we for the Decoy generation we filter all compounds that are outside of this chemical space.
Fantastic. Yeah, I believe probably it was meant to be interpreted that way. We have also a third question. It's not going to be that very short, I believe. I mean, the answer. You mentioned that you've used gold nodes for docking and MOE to rescore some of them. Is it possible to use other nodes? And how flexible the workflow is? How did you build it up for this kind of flexibility? Or maybe even, and that's what I'm adding to this question, maybe even for other projects?
Yeah, so yes, as I want to say, as other workflows, Knime is it's really nice to do this, because so for the gold nodes, you can easily replace them by some SDF reader, or if you have some nodes dedicated for your software, maybe, I don't know if you know plants. I know that there is some node available also, and I'm sure there is other docking software, but at least you can read some SDF files directly from the output of your docking calculation. Then for the rescoring, so I don't really know, but I'm sure you can also, maybe if you have a command line for something open source, you can also easily replace the rescoring nodes by what you want, because it's really the goal of Knime, I think. And for RMSD, I think there is some in CDK or maybe RDKit.
Yeah, fantastic. Thanks for the answer. And we have probably the last question, which is great example of heat generation. What are other computational techniques would you recommend to usually use for it? Well, except of course of SBVS.
I want to say all. Yeah, so
right.
Yeah,
okay.
You can, yeah, maybe for QSAR, I know it's really nice also to do some QSAR modeling. Also I remember I did one workflow for a colleague from biology at Evotec to read some plate, data plate, and to handle some stuff. So yeah, I think we can really use it everywhere.
Okay, fantastic for the thoughts. Emilie, thank you very much for the presentation and answering these questions. I hope you can stay with us backstage and follow the other presentations too. Thank you very much again.
Thank you.